Hello, welcome to Sustainability Modeling, lecture number 8, where we will be discussing the Wonderland Model. The lecture contents, and first we'll talk a little bit about the Wonderland Model, which was introduced by Warren Sanderson in the early 90s. And this model was part of the International Institute for Applied Systems Analysis work that we've mentioned before in this class. Talk about the formulation of the model and the assumptions it makes. We'll see some results and discuss them, and we'll look at the implementation in VENSIM, which will have a separate video. Okay. Now the Wonderland model's got 4 stocks. It's got a population stock that interacts with a per capita output, and this is essentially an economic output per person. Y of t. These interact with a variable that's used to reflect the natural capital, Z of t, or quality of the environment. And pollution is generated, when items get produced. So there's a pollution per unit output that's generated. So we got our 4 stocks, x, y, z, and p, all functions of time. Let's look at the model equations, and one of the things that I'll say right off the bat is that this model it's more heavy on the math, very heavy on the parameters that are used, and as we'll see, these parameters sort of accumulate. But let's take the part model piece by piece. There is a population stock x. The variation of x over time, denoted here by this derivative, or this time rate of change, it's driven by the population itself and then a net growth function. So it's essentially a first order growth model. The function, it's essentially the difference between births and deaths. Okay, that's the population growth rate. And in here, the number of births and number of deaths are tied to the production output, so to the economics, and to the availability of nature or natural capital. Okay, in both cases. And the equations are given here. You can see that these equations are fairly involved. One of the things that I didn't see very clearly in the references, and you can actually look at the original Sanderson paper and the papers that came after that. I didn't really see a very detailed rationale as to why these functions were chosen. There's really not much data to back it up, but again, we'll look at general structure. I want to talk about the parameters later. So let's take a look at these functions. The births are given by essentially this exponential function divided by 1 plus exponential is essentially a function that sort of tapers off, and I'll talk a little bit about this in a second. And the deaths are it's a fairly convoluted function. Let me spell it out in words. The first thing is that population growth, like I said, depends on the per capita output and the level of natural capital. Okay, and both of these are y and z are in the model, so this is an endogenous dependence. Okay, as opposed to exogenous when it depends on external factors. Next thing is that the natural capital Z is assumed to be bounded in the interval between 0 and 1. Z equals 0 means no pollution. C equals 1 means maximum possible damage to the human health and the economy. Okay, and I'll come back to this assumption because I don't think this is quite accurate. It is assumed that both the birth rates and the death rates decrease with increases in net per capita output. So the idea here is that the more is produced, the birth rates will fall down. Okay, and again, I'm not sure what the rationale is for this, which is one of the one of the little criticisms I have about this model. And additionally, death rates rise as the stock of natural capital decreases, and this sort of makes sense. So if there is you know, if your natural capital drops, then your death rates are going to go up. So that's probably okay. Let's take a look at the equations for the next stock. The next stock is Y. Y, it's the production, the per capita output. And again, the time rate of change of per capita output is driven by the capital output, Y itself, and then a function here. Function's got several parameters, but it's essentially a function that is tied directly to the availability of natural capital Z. Okay, and you can see here, and we'll talk about it in a second, that, you know, if and these exponents are positive, so essentially if the natural capital goes up, then the production goes down, and vice versa. Okay, if the natural capital decreases, the rate of production increases. And the functions here are given. There's a pollution control cost that appears, and it actually appears to define you know, this variable Y bar, the net per capita output that appears in the previous equation. So again, not particularly clear of why this formulation, why these forms of the math. Not a fan, as you can as the lecture progresses. You're going to see that I'm not a big fan of this model, but there are some positive things to say though. So let's look at the spelling out some of these terms. So first, the net per capita output is defined as the per capita output minus the per capita expenditures on pollution control. So there is an economic consideration here in terms of the cost of pollution control versus, you know, and how those compare with the economic output. Okay, so this is like the net considers the cost of controlling pollution. The pollution control, in turn, increases with the per capita output. So the more you produce, the higher your cost to control pollution. That sort of makes sense. And this, you know, and of course, it's, you know, if there's a decrease in the natural capital, then of course, you know, the pollution control will decrease. Okay, so that's fine. So the less pressure you put in the environment, the less cost you have to spend to control pollution. That makes total sense. The availability of natural capital influences the growth rate of the economy, because when the environment is totally polluted, so when Z is 0, there's no natural capital, the per capita output shrinks. Okay, if, you know, if Z equals 1, on the other hand, if you have complete availability of natural capital, then you'll see that the you know, the per capita output can grow indefinitely. So this, I mean, this sort of makes sense. So this sort of vindicates a little bit the. I'm going to go back for a second. This vindicates a little bit, you know, the nature of this equation. Okay. I mean, so it's not as obvious, but it sort of works. All right, let's look at now the equation for the natural capital. Okay, now the equation for natural capital, if you look at the very first part, so you have here the change over time of the natural capital, and here you have a sort of a logistics form. You have a coefficient, you have this product of Z, 1 minus Z, and so this is like a logistics with 1 being like a carrying capacity for nature. This is so 1 is the maximum natural capital that can be achieved, and then this you know, so this rate of change of natural capital is multiplied by a pretty convoluted function here. that I wanted to go through, but it's the difference of an exponential and 1, so it's always positive in this case, and actually I shouldn't say that. That's actually not true. It'll be positive as long as this term, which is the term that regenerates. So this term regenerates nature, okay, is higher than this term, which is the pollution component. Okay, so if the regeneration is higher than the pollution production, then nature will grow. If it's the other way around, it may decrease. Okay. This function, on the other hand, so this function that appears here, on the other hand, is also the difference of two things. There is pollution generated by people, okay, and then there's an abatement of pollution that is defined by a coefficient kappa, and this is the ability to abate pollution through technology. Okay, so there is there's cleanup. There's ways to clean up the environment that are considered here, and that's one of the nice aspects that this has. I mean, I'm not a fan of the big formulation, but it sort of has a little bit of logic behind it. So let me summarize this in words. First, the growth of natural capital is logistic, and the speed at which the natural capital regenerates depends positively on the level of natural capital and is negatively influenced by the amount of pollution. Okay, so that's okay. And this is based on the idea that nature has the ability to cleanse itself, but the strength of this ability diminishes as the stock of capital, natural capital, decreases. Since all the model parameters are positive, then the cleansing flow diminishes as the natural capital decreases. Okay, so that's a little bit of what we mentioned already. The difference between these two flows, the cleansing, the polluting, that appear in that F function, are the net effect of natural and human forces on the environment. Okay, so there's a natural ability to regenerate, and then there's the human component trying to clean it up. Okay. And if the actual amount of pollution is above a critical level, the environment deteriorates, and we're going to see that when we push the model simulations a little bit. The fourth stock, finally, is the pollution stock, and the pollution stock follows a very simple sort of exponential decay with a coefficient chi. Minus sign indicates that it decreases over time. Okay, and so pollution, and this is pollution generated per unit of economic output. So it's assumed to decrease over time. And one of the things we'll see with this model is that the model results are very sensitive to not only this assumption, but of course to the value of the parameter chi. And one of my criticisms is to the model is that it really assumes that pollution decreases over time per unit output. I'm not sure that's realistic. I mean, if you think about the logics of the model, you can imagine a scenario in which over time population increases, per capita output increases. The assumption here is that the pollution per unit output decrease, and that assumes essentially that we sort of get better over time at generating less pollution per unit output, and that might be the case, but I don't know that needs to be strictly a scenario that's run. So, but we'll talk a little bit more about this. Now, if you take stock of all the parameters, you'll quickly count that these parameters add up to 20. We have parameters associated with population, parameters associated with the economic model, with the capital output, parameters associated with the environment, and some parameters that are associated more and more with policy, that have to do more with how we do things. And I think this is one of the things that I'll say about this model is that it explicitly accounts for policy items that we can introduce, and I think that's a positive thing to say. I'm not sure that it's that obvious to non-math specialists that these parameters are related to policy. So I think in contrast to the Handy model, which had a lot less parameters and was able to generate a richer set of scenarios, in my opinion, you'll see that this model at least has that going for it, that it accounts for policy parameters explicitly. So this is a schematic, I'm sorry, of the Wonderland model in VENSIM, and you can see, and we'll go in a separate video, we'll go through the model in detail, but essentially you can see how this model is sort of densely packed with all the parameters. But you got your population stock here, you have the output per capita stock, the natural capital stock, and the pollution per unit output stock. Okay, population is driven by the net of births and deaths. Births have got their set of equations. Death's got its own set of equations, and that's why the parameters sort of build up. Some of the death rate, some of the parameters are environmentally related. So the availability of capital affects the deaths in a way, and natural capital also affects the ability of production through the output growth rate. Okay. The output per capita and pollution feed back into the nature ability to regenerate, which feeds into the natural capital equation. And pollution is driven by a single coefficient here, which I mentioned before. So that's sort of the general structure of the model. All the parameters are here. That's how the information flows. I think the other thing that I'll mention is one of the nice things that was done in this model, I think, and at least in the VENSIM implementation, is the use of different colors to identify variables that are associated primarily with one of the stocks. So purple variables in equations are with population, reds are with output per capita, greens are with natural capital, and brown are with pollution. So the choice of colors also makes sense from an intuitive point of view. So that's the VENSIM implementation. We can look at some results when you run the model, and we'll do that in a separate video as well. A base case scenario, scenario 1, has population over time. This is a model that runs for 300 years. Population builds up from a starting value of 1 to almost 4. Even though the model here is people, I think it's more like population units rather than 4 individuals. The output per capita associated with that population growth also grows exponentially. These are in dollars produced per year per person, okay, over time. So these are the stocks X and Y. If we can look at the other two stocks, natural capital in this scenario is pretty much left unchanged. It starts at capacity at 1 and it stays there for the duration. And pollution drops over time exponentially. So I think this is more of and I think it's probably one of the reasons they call the model Wonderland, is because this is a model in which you never run out of nature. There's really very little impact, and pollution goes down over time. So this is like a dream scenario. It's that means population can grow. And one of the things though is that even in this scenario, I'm going to go back to the previous slide. Even in this scenario, population sort of tapers off. So it's not an unlimited growth scenario for population, but it's got population is capped, or at least it sort of tapers off. And we'll see in the Wonderland video for the model running in real time, we'll see some other scenarios that are here. But I wanted to go over some of the simulations that were done in the papers that are in the reading for this lecture. This paper is the paper that was used to actually generate that model. And they run here another scenario, which they call the environmentalist's nightmare scenario, where parameter chi is 0.01. And then in this scenario, look at a variety of stocks. In this scenario, population sort of grows and then collapses very quickly. It sort of reaches a point where it drops. If you look at the associated natural capital here, it's high to begin with, and then it drops. Drops dramatically. Pollution flow, which is it drives the ability of nature to regenerate, also grows and then drops. And you can look at the behavior of other variables as well. Here's yet another scenario. This is a scenario that they call escape for environmental catastrophe, where they put this coefficient of pollution abatement at a value of 100, which is much higher. So this means that the human population is able to abate pollution because of primarily technology much quicker. And then this implies that population can grow and continue to grow. Natural capital drops, yes, but then it starts recovering. And natural capital, I'm sorry, this is natural capital. It sort of drops and then starts recovering. And per capita output again also drops, but then it starts recovering. So this is more of a similar to the handy model in which we saw these cycles of production and drop in production above. One of the things I do in this paper nicely, if you think about population, per capita output production, and natural capital, X, Y, and Z variables plotting over time, you can generate essentially these trajectories. Okay, so if you think about this cube as a space in which X, Y, and Z are coordinates of population, output, and natural capital. And if you plot these over time, you can generate these paths or these trajectories. So essentially, this axis is increasing population. This axis is increasing economic output, and this axis is increasing natural capital. Okay. And so you can look at at each of these scenarios plotted over time. And so if you look at the first one, the economist's dream scenario, that's the very first scenario. It's in the dotted line scenario. It's a little bit confusing to see, but it's a scenario that ends up with a lot of production. Okay, and of course a lot of production with a stable population and a stable natural capital. Okay. If you look at the nightmare scenario, it's a scenario that sort of starts there, and then the natural capital drops very sharply, and then it essentially drops to zero. And the escape scenario, it's one in which you're able to, towards the end, I guess it goes in this way, you're able to produce a lot without depleting too much nature, and population grows a lot more. Okay, so it's a nice way of representing these things, and I thought it'd be useful to show. And this is another paper by the same group of authors, and here they have the same trajectory concept, but they also identify the rates at which. So these are trajectories, but the speed of the model along each trajectory is not the same. So the red portions of the scenarios are faster changes, and the bluer are slower changes. So what these graphs are meant to imply is that is this notion that some of these changes occur very, very fast. So these collapses or these rises in production or in population in some portions may occur slower and faster. So these slow, fast dynamics is something to sort of keep your eye on, because they do have an effect on sustainability issues and how quickly change can occur. Okay, if you want to move from not sustainable to sustainable scenario, you got to think about how long that will take, and so this how long is a very practical question. So we'll look into this concept of slow fast dynamics some more in this class. Okay, and you can actually look at the details of these figures in the papers that were circulating for reading in the class. You can see some nice fast dynamics and some slow dynamics here. This is another of the papers that is in the reading, and this one they take a slightly different set of equations for Wonderland, but it's a very similar model, and they come up with dream scenarios and horror scenarios. Where dream is basically everything, production can go up forever, population can stabilize, so it's sustainable. It's a dream scenario. The horror scenario is production drops, population drops, and of course nature, you run out of nature. Again, sort of the same concept that we've been looking at, and if you look at the time it takes for these scenarios to build up, for the horror scenario to cause a drop in production versus how long it takes for population drops, is much quicker. See, population here drops down in about 100 years plus. The natural capital takes a lot longer to evolve. So these slow fast dynamics, and on the other hand, nature drops very quickly. So these slow fast dynamics, and it's interesting that the times for change are not the same for each variable. So this is an important finding, because this means that the changes in population won't take the same as changes in natural capital, and those two won't take the same change as changes in the economy. So that's something to keep an eye on in terms of the dynamics, is that these changes, even though they're changing together, they doesn't mean that they go together at the same rhythm. Okay, there's this dance between nature, people, and production happens at different rates. Okay, that's an important finding, and that's one of the things that this Wonderland model captures pretty well. See, summarize the results. First, I think the model formulation is simple, but yet it has too many parameters, and I put this in a question mark because I don't want to be overly critical, but as I'll mention in the video for the model, many of these parameters the model is insensitive to, so why have them? I keep coming back to that. Now, once the parameters are introduced, so once you realize that you have 20 parameters, then this model is useful to assess a combination of policies, on the population, on the economics, and technological improvements on pollution and capital output, to look into sustainability scenarios and outcomes. So I think in that sense, it also allows you, the model allows you to do this. And I think the model formulation is very useful to discuss the concepts of trajectories as well as fast-slow dynamics. So spelling here in the well, so I'm going to correct that. Fast-slow dynamics. That's pretty much the discussion for this. So I'll leave it at that. I ask you to read the Millick et al. Paper, which is the paper that this model was originated from, and the other two, which have some of the other results that I mentioned here in the lecture. You can look at the original Sanderson paper in this link, and I actually have the PDF, and I put it on the Dropbox folder, so you can take a look at that as well. And please look at the video of the Wonderland model in VENSIM. Please play around with the model, change things, post your insights and questions on the Facebook page for us to look at and for us to share our insights. Okay, I hope you enjoyed the lecture, and I'll leave it at that. Have a very good week.